Hello everyone! I wanted to make a quick video that shows you how to derive the expression for universal gravitational potential energy. Up until now, we've been using the expression mgh for potential energy. I'm going to call that UG the old way. And that's a perfectly fine representation of gravitational potential energy as long as the value of g is constant and you're moving around near the surface of the Earth where g is not changing substantially. The minute you move far enough away that you have to take into account the changes in the value of g, and also as you get into other situations where, you might just be in space between a few different planets and you're trying to look at how much potential energy you have, and you're not really near any one particular planet or surface, you're near multiple ones, you have to start thinking a little bit more rigorously about potential energy. And so while we're not going to get rid of the UG MGH because that is the best way to calculate your potential energy when G is constant and you're near the surface of the Earth, we need a better expression to deal with astronomical situations or situations where G is variable. I wanted to quickly remind you the tomato should look familiar. Back when we talked about conservative forces, there was a relationship that we relied on consistently for conservative forces, and that relationship was that the work done, the change in potential energy of a conservative force was equal to negative the work done by the conservative force. Gravity, both MGH type gravity, where G is constant, but then also Newton's law of universal gravitation are both conservative forces, so this law applies. So whether we're dealing with gravity near the surface of the Earth, like we did back in an earlier unit, or whether we're dealing with universal gravitation, the change in gravitational potential energy is going to be given by the negative of the work done by gravity. I want to remind you of what that negative sign is, because remember, in the case of lifting a tomato, we know that if I lift a tomato upwards, the potential energy increases. So if my distance is upwards, the change in potential energy is positive. Now, gravity is a force that acts downwards. That's just the weight equals mg. And that force acts opposite the distance. So when I lift the tomato up, gravity actually does negative work because it points against the distance. So the work done by gravity is actually negative. When I combine that with the negative in this expression, that's how I get the positive change in potential energy. So we're going to do something very similar with universal gravitation, but it's going to be, we're going to have to use calculus to do it. Okay, so let's take a look at a situation here of a tomato that's now far enough away from the Earth that we can't be, we have to be a little bit more careful about how we deal with the changes in gravity. So let's say the tomato is initially at a spot R1 and I move it to a space R2. Eventually, we're going to set R2 equal infinity because that's going to provide a nice convenient result. But for now, they're just R1 and R2, so I'm lifting a tomato above the Earth, just from one height close to the Earth to another height further from the Earth. Well, in this case, I have a distance. It's going to be this distance over here. But because the gravitational force, F equals G m1 m2 over r squared, is actually varying over that distance, I have to use calculus. So what I want to think about is my little steps of distance as I move this tomato over this distance. I'm going to be moving it dr each time. And dr, it points in the positive r direction. It points away from the Earth. Meanwhile, the gravitational force is negative. It's actually pointing back towards the planet. And so very similar to lifting the tomato, as I move the tomato away from the Earth, my distance is going to be positive, my force is going to be negative, and the gravitational force should do negative work. Okay, so let's go on now and apply this to the situation of moving the tomato using our expressions for conservative forces. So I know the change in potential energy is going to be equal to negative the work done by gravity. And I know when I deal with a force in general, the work done by that force is going to be the integral of f of x dx between x1 and x2. So in this case, my force is going to be the gravitational force, which is a negative force, and my dx is going to be dr, the distance I'm moving along the radius. So delta UG, and moving from R1 to R2, we'll put limits on this and everything, is going to be equal to negative, and here we're going to have to keep track of like 6 different negative signs, so bear with me, negative the work done by gravity. So there's that negative from here. Oh, I don't want that to look like an equal sign. Let me get rid of that. But that negative, which is the negative from the conservative force equation, is going to be the integral from R1 to R2, the gravitational force, which is negative GMM over R squared, because it points in the negative R direction, dr. So the first thing you will notice here, just like before, those two negatives cancel out. That's great. I'm going to get another one in here from the integral, because I can rewrite this, delta UG equals, the GMM part is constant, so I can just take that out, and it's the integral from R1 to R2 of 1 over R squared dr. Now you might remember the integral of 1 over R squared dr. I'll write it down here by the tomato. The integral of 1 over R squared dr in its general form is equal to negative 1 over R. You add 1 to the power, so negative 2 becomes negative 1, and then you divide by that. That's where this negative comes from, and then it's negative 1 over R. So this integral is equal to GMM times negative 1 over R evaluated from R1 to R2. So let's work that all out, subtract the limits. So delta UG is equal to negative GMM over R2 minus negative GMM over R1. And if you trace back, do the algebra out over here, you'll be able to see, double check the negative signs. So what that winds up becoming, now I can erase this so I have room, is GMM over R1 minus GMM over R2. Okay, and that's my delta UG. I'm going to go to a new page, just so I have a little more room. So the previous result was that delta UG was equal to GMM over R1 minus GMM over R2. Now that seems fine. For the delta UG, I'm going to represent that in terms of my UG at R2 and my UG at R1. I don't know why I have an extra parentheses. Let's get rid of that. So delta UG is going to be UG at R2 minus UG at R1, and that's going to be GMM over R1 minus GMM over R2. Now here's the cool part. We're going to set R2 equal to something. And so one of the things that you have to do when you deal with gravitational potential energy is you have to define a zero. When we were dealing with the surface of the Earth, we always defined the lowest point to be 0, so all your potential energies were positive. You could have been more paradoxical and said, I'm going to define the highest point of my roller coaster to be height equals 0, and then all other heights were negative, so you'd have constantly negative potential energy. And that seems weird for that situation, but it turns out it's actually really useful for this situation, for this particular situation. Physicists have to decide, where are we going to call the zero of potential energy? And you have a lot of options: the surface of the planet, the center of the planet. What if you have two planets though? Whose center do you use? Whose surface do you use, right? So it gets a little complicated. So everybody, physicists across the world, kind of universally agree that we are going to actually do something a little weird. We're going to define the zero of potential energy to be at infinity, at R equals infinity. That's appealing for two reasons. One reason is because when R equals infinity, the force is also equal to 0, so it's nice to have the potential energy also equal to 0. Another reason is that means that you've kind of chosen your highest point to be the 0 point, so all your potential energies that fall underneath that are now also negative. And gravitationally, potential energy is kind of like a binding energy. So to think of it as a negative potential energy, meaning you have to climb out of this hole, actually makes a lot of intuitive sense. So if we set R2 equals infinity, and we define that u at infinity equals 0. Let's see what this equation reduces to. Let's also set R1 just equal to the more general variable R. So what I'll be left with is just kind of an expression for the potential energy relative to the 0 being at infinity of a given distance R from the sphere. So UG at R2, which is infinity, minus UG at R is equal to GMM over R minus GMM over infinity. Well, 1 over infinity is tiny 0. We already defined UG at infinity to be 0. So I'm left with my general equation. UG, negative UG of R equals GMM over R, or more importantly, UG as a function of R was equal to negative GMM over R. And that is the expression for gravitational potential energy. So finally, we have this new expression, UG of R, which is the potential energy of an object at distance r away from a spherical mass, is equal to, or point mass, is equal to negative G times the big mass times the little mass over R. If, one mass isn't little and one mass isn't big and they're both like two planets, you could still use this equation. It's just the potential energy of that system, which is a great way to think about it. And you really are always calculating a potential energy of a system. When one of the masses is tiny, we sort of loosely call it that mass's potential energy. Realistically, it's the potential energy of the system. And what's great about this is you can use it in place of where you use the old MGH. So if you're looking at like an asteroid falling to the Earth and it's converting potential energy into kinetic energy, and we know MGH is going to break down because G is going to change over those distances, what we can say is still the old-fashioned Ki plus Ui equals Kf plus Uf. But now Ki is going to be 1/2 mv initial squared. Ui is going to be negative GMM over the initial distance from the planet. And that's going to be equal to Kf, which is 1/2 mvf squared plus negative GMM over R final. Sorry, R final, not R final squared. That is a habit that is unfortunately going to happen to all of us. Okay, so that's really the new and improved version of energy conservation. What I will say is negative GMM over R doesn't give you the same answer as MGH close to the surface. And that's because close to the surface, we define the surface as potential energy 0. But in this case, we're defining infinity as potential energy 0. What it will do, though, is if you go over a height difference, the change in potential energy will match regardless of what equation you use. All right, everyone, that was a lot, but I hope it was helpful. Please watch this video, and then when you try the problems, this is how you're going to approach the energy transformation parts of those problems, and we'll talk about it in our next class.